All right, welcome back. Today, Chapter 4, Section 2.1, Splitting Fields. We'll start with a simple example. The polynomial x squared plus 1 is a polynomial with real coefficients. And of course, as you know, it has no roots over the real numbers. And this is very frustrating for a lot of applications when your polynomials don't have roots in your base field. It just makes things much more difficult. And so it's often easier to pass to a field where there are roots and solve the problem there, and then to try to go back to your original field afterwards. So the field that works for us, that lets this thing factor, is when you attach I. In that case, it factors. So attach I, of course you get the complex numbers, and then it factors as x plus I and x minus I. Maybe remarkably, we're going to see that you can always do this. Let's start with some definitions. All right, let's look at two fields, f contained in K. A non-constant polynomial f in f of x. We'll say the degree of f is n. Now we'll say that K is a splitting field for f over f if two properties are satisfied. Number one, that f is a product of x minus alpha i's times a constant. The Cn has a subscript n just because if you look at the expression here, that Cn will just be the leading coefficient. So of course Cn has to be in the field f, and each of the alphas, alpha 1 through alpha n, have to be in K. I mean, they can be in f, but certainly they have to be in K. And so the point is, f splits as a product of linear terms. All right. Number two is that K is equal to f adjoin alpha 1 to alpha n. In other words, K is the smallest field over which f splits into this product of linear terms, because I've just started with f and added the bare minimum necessary, the alphas, the roots. So you should think of number two as a minimality condition. Number one as the actual factoring condition. So more generally, if just number one holds, whether or not two is in place, we say that f splits over K. All right, let's look at some examples here. So first example is the one we already started, that the complex numbers is the splitting field for x squared plus 1 over the reals. Here I wrote it kind of pedantically that C is R attach I and minus I. Of course, once I attach I, it's redundant to attach minus I. But anyway, to verify that it is indeed the splitting field, then we have to write it that way. All right, new example. So this is kind of a cop-out. It's almost the same type of example. Q attached I is the splitting field for x squared plus 1 over Q, because I took the two roots of that polynomial and attached them. By the way, you keep hearing me say the splitting field. We will prove that essentially up to isomorphism, the splitting fields are unique, but we have not shown it yet. All right, another example. Q attached root 2 is the splitting field for x squared minus 2 over Q. And technically, you should note that this is the same as Q attached square root of 2, comma, minus square root of 2. So I attached all the roots. However, just attaching square root of 2 does everything we need. So as a final comment here, x squared minus 2 splits over the reals, because it factors. The reals contain the square roots of 2. And it's not the splitting field, though. It's strictly bigger, because as we've already seen, that's just Q attached the square root of 2. And that is smaller than R. Okay, first theorem. All right, let's start with f in f of x. The degree has to be at least 1. Degree 0 polynomials, of course, don't have roots, or they're just 0, in which case they're all roots. Anyway, degree at least 1. All right, now we don't even know that there are extension fields where there's a root. So part one of this theorem is that there is an extension field that has a root of the polynomial f. And when we attach it, we get now a field that has a root of f in it. In number 2, we'll use number 1, and we'll show that, in fact, always splitting fields exist. This is a fun proof. I actually remember this as an undergraduate, and in hindsight, it's one of these trivial things, but the first time I saw it, I was really impressed. It was just a cool idea. I mean, how do you find a root somewhere, just, you know, sitting out there in this vacuum of all these possible fields? Anyway, there's a trick. So, start with h, an irreducible factor of f. In f of x. Here we're using that f of x is a unique factorization domain, so factor it out, it's got to have some irreducible piece. All right, first of all, if the degree of h happens to be 1, then it's this linear term, ax plus b, and so you can take alpha to be minus a inverse b, and you've got a root. In this case, the root is actually already in your field f. So E is equal to f in this case, and then there's nothing to do. So let's go on to the case where the degree is at least 2. Okay, this is where we earn our money. We need to create out of nothing a field that has a root of the original polynomial f, but it's enough to find a root of h, since a root of h will also be a root of f. So here's the trick. Start with the polynomial field, f of x. We want to kill h, that is find a root, so mod out by h. Okay, let's let that be E. Now, of course, this won't be helpful at all unless E is a field. Okay, since h is irreducible, since we're working in a UFD, that means h is prime. Since we're in a PID, that means that the ideal generated by h is maximal, and since it's maximal, that means E is a field. So E really is a field. So moreover, we can view F as a subfield of E by identifying F, C and F with C plus H and E. You can see this is an injective map, homomorphism, and this is an embedding of F into E. And so that makes E an extension field of F. All right, let's see what this gets us. So let's write n for the degree of h. By the division algorithm, any polynomial g in f of x, you can divide out by the h here. So you can write g as hq plus r, where the degree of r is strictly less than n. All right, so once we've divided out by h, and since h is 0 in E, we get that g plus the ideal generated by h is the same as r plus the ideal generated by h. In particular, the images of 1, x up to xn minus 1, they'll span E over f. In particular, if we let alpha be x plus h, then, of course, rewriting the spanning set here, 1 is already in f, at least under our identification with f as a subset of E. Then x plus h, that's just alpha, and the next term is alpha squared, alpha cubed, all the way up to alpha n minus 1. In particular, we see that E is just f, again, f embedded in E, is just f attached to alpha. Moreover, I claim alpha is our root of h. All right, so to check this, we just need to plug alpha into h. And how do you do that? I mean, alpha is just like x, it's x plus h. And if you plug it in everywhere and do your arithmetic in the quotient, you just get h of x plus h, because again, alpha behaves just like x everywhere, but you've got this extra extra ideal generated by h floating around everywhere. But since h of x is, of course, in there, that's just h. And if we write this more explicitly, that's 0 plus h. In other words, and this is when we, remember, said how we identify elements in the field, this is just corresponds to the element 0 with our embedding of f. So h of alpha is indeed 0. And since h of alpha is 0, of course, this gives that f of alpha will be 0 too. All right, so that's part 1. We still have to do part 2. Okay, here. All right, so we still have part 2. Okay, by part 1, let's call the field we constructed E1, and the root we constructed alpha 1. And what we have so far is that f has a root, alpha 1, in E1. Okay, since f has a root in E1, then x minus alpha 1 divides it. So write f as x minus alpha 1 times something else, f1. And this f1 will have be a polynomial in E1 of x. Now, if this f1 is degree at least 1, then we're just going to repeat. So, by the same argument, there's a field E2 that contains E1, and there's an element alpha 2 in E2, so that E2 is just E1 adjoined alpha 2, and alpha 2 is a root of f1. Since alpha 2 is a root, then x minus alpha 2 divides out, so f1 is x minus alpha 2 times f2. Putting everything back into f, this gives us a nested set of fields, f contained in f adjoined alpha 1, and then adjoined some alpha 2, both of which are roots of f. And then f factors as x minus alpha 1, x minus alpha 2, f2. Now, of course, the degree of f2 is going to be 2 lower than the degree of f. If the degree of f2 is still bigger than or equal to 1, we'll just keep repeating. And each time it's going to knock down the degree by 1. So the procedure will eventually get us down to a constant polynomial. So here's what we get. All right, here it is in all its glory. You've got a whole bunch of nested fields where you keep attaching zeros of f over and over again until you get all the way up to n of them, where n is the degree of f. So the roots are alpha 1, alpha 2, alpha 3, all the way to alpha n. Again, just repeating the same procedure we've done. And then f factors as a product of all these x minus alpha i's. X minus alpha 1, x minus alpha 2, all the way to x minus alpha n. Times some other polynomial, f sub n plus 1. Now this polynomial has coefficients in the final field, f of alpha 1 to alpha n, attach x, but its degree is 0. All right, so if you take this expression here and think of multiplying it out, it's obvious, since we just have x's here and here and here, and an fn plus 1 there, that's degree 0. This has to be the leading coefficient of f, because it's the coefficient of x to the n. Since f was originally in capital F of x, that means fn plus 1 actually is in the field f. And now we have split f, and by construction, this field here was the minimal field because we only attached the roots. And so we've shown the existence of a splitting field. And that's the end of the proof. All right, we get a corollary out of this proof, so let me write it down. Okay, here's the statement. If you start with a polynomial f in f of x, degree at least 1, and k is a splitting field for f over f, then the degree of k over f will be less than or equal to n factorial. So the proof goes like this. Using the definition of a splitting field, we have all the roots of f, alpha 1 to alpha n, in k, and k is just f attach alpha 1 to alpha n. But then we look at this chain of inclusions for fields. So here's the chain where you attach one root at a time, first alpha 1, then alpha 2, alpha 3, and so forth. First of all, f kills alpha 1. So that means the degree of the minimal polynomial is at most f, divides f in fact, but in particular it has degree at most n, so the degree of this first extension is at most n. And this, just as above, then since you have a root in this first field, you can write f as x minus alpha 1 over this first field here, where f1 is some polynomial there. Since f1 kills alpha 2, which will be the next root, then in its degree is, the degree of f1 is n minus 1. That means the degree of this minimal polynomial is at most n minus 1. So the degree of this extension is at most n minus 1. And then you just keep going this way. This will have degree at most n minus 2 and all the way down. So then by the multiplicativity of degrees, the degree of the whole extension here, as you see, will be less than n times n minus 1, n minus 2, all the way down. And you'll get less than n factorial, which will be the proof of the corollary. All right, so that's that. All right, as kind of an example, but more of a warning, this gives us an upper bound for splitting fields where the degree of the extension is at most n factorial. And generically that's true, but in any particular case, usually you get a smaller number. All right, let's start with x to the p minus 1. This is over q. So here p is a prime, and of course this always factors. 1 is a root of it, and therefore you know it. X minus 1 will factor over q, but in fact this is what you get, this beginning of a geometric series type thing. All right. Okay, so if you remember, there was a homework problem. If you do linear changes of change of variables, it didn't change the irreducibility. And you did this problem in your homework. But if you change x to x plus 1, then it becomes amenable to Eisenstein. You Eisenstein it and see that it's irreducible. So this polynomial here is actually irreducible over q. And then if you ask about its splitting field, well, you know what the roots are, because the roots of f are also roots of x to the p minus 1. So you know how to do these. And in fact, if you just attach sort of the smallest angle one, it is obvious that you get all the roots. So here it is. You just attach e to the 2 pi I over p. It's clear as you multiply this, you get all the other roots. So since this was irreducible, it is, and monic, it is the minimal polynomial. So the degree of the extension of k over q is p minus 1. And as I said, that's the splitting field for a degree p minus 1 polynomial. And that is, of course, in fact, it's also the splitting field for x to the p minus 1, because 1 is already in there. In any case, this is much, much smaller than p factorial or p minus 1 factorial. So that corollary, even though it's true and it is useful, it, in many particular cases, is a huge overkill. All right, next on our agenda, now that we have existence, we want to turn to uniqueness. And that is going to come from the following definition. Let's start out with the field F as a subfield of two other fields, subfield of E and subfield of K. We'll say a map from E to K is an F isomorphism from E to K if, first of all, it's an isomorphism of fields from E to K. The addition is that phi restricted to F is the identity map. You should think of these as the generalization of linear maps of vector spaces. There's also a good commutative diagram, I guess you should always have in mind. Here it is. F sits in both E and K, so there's an inclusion map from F into E. It just maps, x to x. And saying that phi restricted to F is the identity map just means that this diagram is commutative. You can start up here and head this way, go directly to K, or if you're down here at F, oh, I said that wrong. So let me erase that. If you start down here at F, you can go up to E by inclusion, and then over with phi to K. Of course, since phi is the identity on F, this will just be mapping sort of x to x to x. And you get the same answer if you just include this way. That's the commutative diagram. All right. In the special case that E is K, then phi is called an F automorphism. And these are going to be really important. This is going to be what we call our Galois groups in a little bit. There's a part 2. When there is an F automorphism from E to K, then E and K are called isomorphic extensions. And this is going to be the sense in which splitting fields will be unique. Any two splitting fields we'll see below are going to be isomorphic by F isomorphisms. Alrighty, so we're going to start with a reminder of a lemma that you proved in your homework. It's pretty straightforward, but we're going to use it a lot. Alright, so start with an isomorphism or homomorphism or isomorphism, either case, phi from two fields, F1 to F2. Then we're going to get a homomorphism slash isomorphism, respectively. We'll call it by the same name because it's an extension of the original phi. So phi going from polynomials over f1 of x to polynomials over f2 of x. Simply applying phi to the coefficients. So here's the formula there. Phi on the sum of ck x to the k is just the sum of phi applied to ck x to the k. And of course, if phi happens to be an isomorphism, then the original polynomial is irreducible if and only if phi of f is irreducible. So we're going to use this lemma a number of times in the next theorem. In this theorem, we're going to do in a much more general fashion than we need just to get the uniqueness of the splitting fields, because this theorem is going to be used a lot in our Galois theory as sort of the bread and butter. Let's start with two sets of fields contained in each other, F1 in E1 and F2 inside of E2. And then let's start with an isomorphism phi going from F1 to F2. Throughout this, H and F will be non-constant polynomials in the original field, F1 of x. And by this lemma from the homework that we mentioned, we're going to also use phi for the name of the homomorphism that's extended from F1 to F2 to the maps on the polynomial rings. All right, so that's the general setup. We're going to have three separate parts to this theorem. Part 1. So part 1, we're going to start with an irreducible polynomial, h in F1 of x, and look at its corresponding polynomial, phi of h in F2. It'll still be irreducible. And the extra assumption here, besides the irreducibility, is that we have a root, alpha 1, in E1 for h. And we're also going to assume that there is a root of phi of h in E2 called beta. All right, irreducible polynomials. Supposing E1 has a root of the first and E2 has a root of the second. Okay, then the point of 1 is that it's going to give us an isomorphism. We'll call it psi, that goes just to F1 attached alpha to F2 attached beta. So these will be isomorphic fields, but it's also got to have two extra properties that will be important. The first is that psi of alpha is beta, so it takes the root of h to the root of phi of h. And the second condition is that we have this really handy commutative diagram. We already know how to map from F1 to F2 with phi. F1, of course, by inclusion embeds into F1 of alpha, and F2 embeds by inclusion into F2 of beta. And the map we're looking for, psi, goes on this top row here from F1 to alpha, F2 of beta, and it makes everything commute. So you can start here down at F1, include it, map it over with psi, or use the little phi and map it over to F2 and then include that, and you'll get the same answer. Okay? All right, so I wrote down here sort of the equation that says commuting. If you think about it, it just means if you take this top row psi, restrict it to the constants, F1, you should get phi. That's all it means. All right, and of course psi had to be an isomorphism, and it took the alpha to the beta. All right, that's part 1. There's a part 2 that's about as long as this, so let me leave this up just a second so you can get it. You should think of part 1 as sort of doing what part 2 does in general, except part 1 only does one root at a time. Part 2 is going to go up to the whole splitting field. All right, let's move this up and get up here to part 2. In this case, instead of starting with an irreducible polynomial, we're going to start with any old f. But the added assumption now is that E1 is the splitting field for f, and that E2 will be the splitting field for phi of f. And then, just as in part 1, we assert the existence of an isomorphism of fields, capital Phi, that now goes from E1 to E2, with also some commutative diagram assumption as well. So, we have F1 included in E1, F2 in E2, and this diagram should commute. You can start in F1, view yourself as if you were in E1 by inclusion, apply capital Phi, and then wind up at E2. Or you can use little phi to go directly across to F2, include that into E2, and you get the same answer. So here I've written out what the commutative diagram means, just in symbols without a picture. It means if you take capital Phi and restrict it to the base field F1 there, that's the same as just doing little phi. All right, so I'll let you copy that. This one also will use a lot. We're going to use 1 and 2. Both of them kind of are useful in their own right. Of course, it's pretty easy to see we're going to use 1 to prove 2. All right. Number 3. Number 3 is the reason that we started off with this. That says that any two splitting fields are isomorphic. Isomorphic extensions. So, anyway, looking at 3, you can see we'll get 3 from 2 for free in the special case where the little phi is just the identity map. When little phi is the identity map, then we have the fact that any two splitting fields are isomorphic extensions. In fact, it's pretty common throughout all this business that phi is the identity map. All right, let's turn to the proof. Number 1. Actually, let me do this instead. Let's start from the beginning. What I just said, we'll stick it in here so then we don't have to mention it again. If we have 2, then we get 3 for free. In the special case where F1 and F2 are the same, and phi is just the identity map. Next, I claim that if we've done 1, we're going to get 2. The argument will proceed by induction on n, the degree of f. If n is equal to 1, then we already have the root there. So the splitting field is the base field, and so the capital phi is just the little phi, and there's nothing to do. Otherwise, let's let h be an irreducible factor of f, and now you see how we're going to use part 1. By the definition of E1 being the splitting field for f, E1 is f attached some alpha 1 to alpha n, where these alpha I are the roots of f. All right, since E1 of x is a unique factorization domain, when we write f as the product up to a scalar of all these x minus alpha i's, and separately we write out it as a factor of h times something, we can rearrange all these terms so a bunch of these x minus alpha i's up to scalar has to be an h. So in particular, one of them has to be a factor of h. We can reindex, so that's x minus alpha 1. In particular, alpha 1 is a root of h. All right, we're going to do the same story now looking at phi of h and phi of f. All right, let's let the beta i's be the roots of phi of f in E2. And same argument, we index them, so beta 1 is actually a root of phi of h. All right, now we use part 1. Okay, let's let capital psi be the isomorphism from f1 of alpha 1 to f2 of beta 1 that takes alpha 1 to beta 1, and it extends the map phi on the base fields. All right, now it's time to start using our inductive hypothesis. First of all, E1 is still a splitting field for f divided by x minus alpha 1. That, of course, is a polynomial in f1 attach alpha 1, because alpha 1 was a root, so it divided. And it's still a splitting field because E1 was f attached alpha 1, alpha 2, alpha 3, alpha 4, all the way on. And I've already got my alpha 1 here, but I don't need it anymore. And I'm still attaching all the remaining roots of f. So it's exactly the splitting field for this polynomial over a larger base field. Okay, but this polynomial now is degree 1 less. So the inductive hypothesis applies. And we just apply it to this larger base field. So that means we can extend psi to a capital phi going from the splitting field E1 to E2. Extends the original map psi, but of course there's a lower part of this. Let me draw it. Remember, the way we constructed psi was as an extension of phi. So now capital phi extends psi, which extends phi. So of course capital phi extends little phi as well. And now we have the existence of capital phi just like we wanted. So everything comes down now to simply part 1. So let's turn to that one. All right, so now we've got h, an irreducible polynomial, and we want to extend phi up to cover just one root. We see, of course, since h is irreducible, it'll be the minimal polynomial, at least up to scalar. In particular, this field f1 attach alpha, as we already know, is the polynomial ring f1 attach x mod out by the ideal generated by h. Now remember, we had the original isomorphism phi going from f1 to f2, and the corresponding extension phi to the polynomial ring from f1 of x to f2 of x. This is an isomorphism as well, and now we're just going to have it descend down to the quotient in the obvious way. So here's the definition. Phi bar will go from the quotient f1 of x mod h to f2 of x mod phi of h, just by mapping f plus h to, just applying it to the representative, phi of f plus the ideal generated by phi of h. So is this an isomorphism? Is it well defined? The way to see this is to start with the following. Start with phi, as we've already said, going from f1 of x to f2 of x. That's an isomorphism. And then project f2 of x onto the quotient f2 of x mod the ideal generated by phi of f. So it's a composition of homomorphisms. We get a homomorphism. Each one is surjective, so it's surjective. So what is the kernel of this map? Well, if you think about it for a second, who dies here? These are all the polynomials that go into this ideal here. And obviously, the way you land there is to start with anything in h, apply phi, so you get to phi of h, and then project down. So that's the kernel. And then the first isomorphism theorem tells us, therefore, that this map is an isomorphism, because I just modded out by the kernel. And this map phi bar is just the induced map, if you look at how we defined everything. So that's that. This phi bar is actually an isomorphism. And of course, this will finish the argument. So we get this big diagram here. F1 is included into F1 of alpha. There's the isomorphism to F1 of x mod h. And then we use this phi bar to go isomorphically to F2 of x mod phi of h, which goes isomorphically to F2 attached alpha attach beta. And I claim this composition here is, we're going to call it our psi, and that is the psi we wanted. So how do we know that it's the right, does everything we wanted? Well, first of all, isomorphism is automatic because everything on the top row is an isomorphism. What's left to check? Well, where does alpha get mapped to? Well, alpha is up here, and this first isomorphism, if you remember how it's done, that just sends alpha to x plus h. That was our construction. And then we hit phi bar on it, and phi bar just sends it to phi of x plus phi h. But the phi just is applied to the coefficients here, so it's just 1. So it's x plus phi h. And then we go to the last isomorphism, and again, the isomorphism, when you attach a root, if you look back again to the proof, that went simply to beta plus phi h. Oops, no phi h there. I'll erase that. It just went to beta. So that's the first thing we needed, that capital psi really took alpha to beta. And you just had to follow all these isomorphisms. What about, is it an extension of little phi? All right, so let's start with C and F1 and see where things go. Well, C is a constant here, and so it gets mapped to just C plus H. That's the first map. And then you have to hit it with phi bar on the top, so that's just phi of C plus phi H. And where does that go? Remember, these are the way you do this is just you evaluate the polynomials at beta here, but it's a constant, so it just goes to phi of C. And that means that capital psi does the exact same thing as little phi on the base field, which is the last condition we needed. So that'll end the proof. Okay, so that's our big theorem. I'm going to use that heavily in the next section. For now, let's turn to a final piece of the puzzle we need for the next section, and that'll be normality. So here's the definition. Let's start with F contained in E, a field extension. That's an algebraic extension. All right, we're going to call E a normal extension of F if any irreducible polynomial, f and f of x, that has one root in E actually splits in E. So if you're irreducible, you've got one root there, all of them are there. That's what a normal extension is. It seems unbelievable, I guess, at first when you don't have much experience with these, but this would seem to be super powerful and super rare. But it's not as rare as you'd think, and we actually will have a really good idea of when this happens. All right, soon we're going to be attaching some subgroups to field extensions, and we'll see that the subgroup is normal if and only if the extension is normal. And that's why this definition is called normal, because eventually there will be some groups in the picture, and it corresponds to normal subgroups. This is actually a type of idea that comes up a lot in math. For instance, if you look at covering spaces, you can talk about holes in the spaces, and there's a fundamental group that controls that. And then you can talk about covering spaces. And again, what will happen is you'll have a normal covering space will have to do with this corresponding subgroup being normal in the fundamental group. So this theme comes up a lot, that somehow if you can attach algebraic invariance to things, that normality is often measuring something geometrical or something important. All right, let's at least do an example. Our first example is simply R contained in the complex numbers. This is normal because by the fundamental theorem of arithmetic, every polynomial splits. So that's that. Let's have a non-example. For this, let's consider Q contained in Q attached, the cube root of 3. This will not be normal. For our example, we'll look at x cubed minus 3 over the rationals. It's got one root, of course, in this extension, the cube root of 3, but no other roots since they're both complex, and in particular not real. All right, let's go on to our theorem. Let's start out with the field f contained in an extension k. And the statement is k is a splitting field for some polynomial if and only if it's a finite normal extension of f. So at least for finite extensions, this completely tells us how to handle normality. All right, let's turn to the proof. We've got two directions to prove. Let's go to the right. Since k is a splitting field, it just attached a bunch of roots, and so of course that's finite. Okay, the hard part is to show that it's a normal extension, that if it gets one root, it gets them all. So suppose g is an irreducible polynomial, and g has a root beta that's in k. We need to show that g actually splits over k. Okay, we know there is a splitting field, so let's call that E. The trick is to look at the splitting field for g over k. Not over f, but over k. Of course, then we have f in k in E, and what we really want to show is that E is the same as k. In other words, that it actually was splitting over k. Okay, and to this end, remember, you get E by just attaching to k roots of g, so it suffices to show that whenever we have a gamma in E that's a root of g, then actually the gamma was already in k. So that'll prove this part of our theorem. All right, let's consider these two chains of ideals, f in f attached beta, the original root contained in k, and then f contained in f of gamma, the new possible root contained in, well, it might not be in k, so k attached gamma. Now, we already know with this previous theorem how to kind of go back and forth between attaching different roots. Beta and gamma are roots of the same g, and it's irreducible. So we can use that previous lemma there. And then to finish it off at the end, we're going to use some results about splitting fields. So also that previous lemma to finish things. All right, so let's go ahead and start. So by the previous theorem, there is a map that goes like this. An isomorphism psi. Psi will take beta to gamma because these are both roots of the irreducible h, and it'll make this commutative. In other words, psi is an f map. Okay, now we're going to see if we can move up to the next level with the k and the k of gamma. And we again want to use that previous theorem. We already used the part where you attach a single root to an irreducible, but now we want to use the thing about splitting fields. So let's make some notes. First of all, k is a splitting field of f, so it's f attach the roots of f. Now beta is an f, so if I attach that as well, I don't gain anything more. It's just still an equality, and that lets me rewrite it this way. So that means this is f of beta attach the roots of f. So that means k is a splitting field over f of beta for f as well. Okay, so going from f to k, splitting field, but also going from f of beta to k, still splitting field. Similarly, by essentially the same argument, k attach gamma is a splitting field for f over f of gamma. Same argument. So now we can use that lemma again to further extend our diagram. Okay, so we've got this whole diagram now. So starting at the base here, we have an isomorphism down here in the middle, and they're contained in these two fields. They're both splitting fields for f. So there is an extension, this top dotted line here, psi, that gives an isomorphism. So we have an isomorphism, and when I restrict it to f of beta, it's that original psi. In particular, when I restrict it to f, it's the identity. Okay, Now, it's obvious that F isomorphisms preserve bases over F. All right. This gives us... All right, so if K and K gamma are isomorphic under an F isomorphism, therefore they have the same dimension over F, so the degree of K over F is the same as the degree of K of gamma over F, but by multiplicativeness of chains of fields, we get that we can go from K of gamma down to K and then down to F, so we get this product, and of course we can divide out by those. This gives us that this dimension here is got to be 1. So these two fields are the same, so gamma is in K, which is what we set out to do. All right, that ends to the right, which leaves to the left. Since K is now a finite extension, that means we attached alpha 1 through alpha n, some algebraic elements. Let's write f sub I for the minimal polynomial for each of those alpha i's, minimal polynomial over f, and let just plain f be the product of all those f sub i's. Since K is normal and f sub I is minimal, it has one root in there, it has all the roots, so I can throw in all the extra roots without making the field bigger because they're already there. So in fact, K is f attach all roots of f1, then all roots of f2, and all roots of fn. This means that K is just f attach all roots of f, and that means that K is a splitting field. And that is what we wanted to do, so that's the end of that proof. Okay, I guess that's it for this section. All right, that's the end.